All right, welcome to this presentation on dynamic programming. Well, more specifically, recurrence relations, which are actually more general than dynamic programming. But that's going to be our main focus today. I've named today's lecture The Timeless Way of Building the, inspired by Christopher Alexander's famous book, The Timeless Way of Building, in which he talks about how patterns are made out of nothing more than just other patterns, and how things are also actually made out of patterns as well. Anyway, today is going to be about recurrence relations and dynamic programming, not so much philosophy or architecture. So the goal of today's presentation is we're only going to practice recognizing patterns for recurrence relations when dealing with certain problems that you might deal with. A lot of them, we'll be going over a lot of LeetCode problems basically today. And you're also going to have the chance to write recurrence relations. A good way to use this presentation today is to actually pause the video. This is actually re-recorded because the live one actually, my computer crashed, and there are a lot of settings that weren't good with it. But yeah, I encourage you to pause the video and try and write the recurrence relation yourself. Today is going to be, I'm basically going to present a bunch of different patterns, and then we'll look at problems, and you're not necessarily going to have to write the code for it, but you should try and figure out which pattern, which kind of recurrence relation fits with that problem. Some of the things that we're not going to do is worry about getting the code 100% correct. We're also not going to worry about maybe having the most, well, I'm not going to worry about having the most precise notation. In fact, I'm probably going to abuse some notation as well. And we're also not going to worry about a tabular approach to problems, which is another style of dynamic programming. I'm also not going to talk about minimizing space complexity this presentation. And I'm going to deal with simple recursion only. So basically a function A calls a function A. We're not going to have some kind of cycle like A calling B, calling C, calling A, etc. All right. So I use my own notation here, but you should maybe help me correct my mistakes if I say something wrong. I would love to get some comments, or just send me, email me that I made a mistake. And I'm actually going to focus as using depth first search as the main vehicle for implementing a dynamic programming approach. But you should recognize, of course, that recurrence relations are more general than dynamic programming, and they're more general than depth first search as well. You've already seen dynamic programming phrased in terms of Dijkstra's algorithm, and there's also greedy algorithms that are also based on recurrence relations. Recurrence relations are really a huge topic in and of themselves. And if you think about computer science, the most interesting things about computer science are really how you take a certain type of problem and you break that down into smaller computational steps. So yeah, very general stuff today. So we're not going to deal with too many really like very specific details about particular problems. But you will see accepted code for a lot of these. And I might also point out to you some code that doesn't get accepted. And remember, for these problems, there are multiple recurrence relations that are possible. If you find other recurrence relations than the ones that I present, that's great, okay? But I'm just going to present the ones that I'm most familiar with, ones that I feel like fit into a lot of different types of problems that you might see on LeetCode, or actually even in the wild when you're doing real-life software engineering. But I mean, in most cases, for most software development, you just grab a library, right? But it's still useful to understand algorithms in order to choose which libraries you're going to use and make the design decisions. And hopefully that's what you take away from these presentations. It's not really about just the algorithms. It's about making design choices. All right, so let's talk about common recurrence relations. I'm going to go over some 1D recurrence relations, or recurrence relations that happen over an input of one dimension. And then I'm going to move on to some 2D ones, and there are also going to be some other ones that I cover where we look at divide and conquer a little bit. There's a common knapsack pattern, and there's also stuff with grids that are a bit more specific. And we're not going to talk about some of these other patterns. And then we have some practice problems. All right, so let's jump right into that. So, oh yeah, this is one thing I wanted to mention. Sometimes you're going to see basically a problem. You're going to read it. And then you kind of just know what recurrence relation pattern that is going to fit the problem. Okay. Other times you're going to deal with a problem and you're just going to be wondering what. But luckily, you'll have a bunch of recurrence relations that you know that may or may not fit the problem, but they are things where you can try and apply them and see if maybe that avenue of thinking works, maybe it doesn't. And hopefully you use these different patterns to further reinforce your learning and your own understanding of how problems can be broken down. Make those good design choices. All right, so here's my own terminology before we get started. And just note that I'm going to be abusing notation. If there's better notation or somewhere where you've seen this better described, again, email me or leave a comment somewhere. So, like with the Fibonacci's, I would say that f is the primary recursive function, and if we have fi, well, we have f of I minus 1 plus f of I minus 2. And this is our primary recursive function, and I use notation like this where I have like an open interval with a bunch of numbers in it. I mean to take f over each element of this interval, where you'll end up basically with a mapping of f over this domain, essentially. G is very vague. It is some operation to combine results. In this case, this G is our just addition, right? It takes two results, and all it does is just add them, right? So for Fibonacci numbers, this G looks very simple, but there's going to be a lot of times when I write G to mean something much more complex. It could be maybe a hash table lookup, maybe like within a for loop or something. Very, very general, very loosely defined. And deducing from above, you could see that, hey, if I took G over this basically range of results, these mappings, I'm going to basically get some way to combine all these different results. So G might actually be a max operation. It might be doing a max over different recursive calls of F0 or F1. Anyway, I'll point out this what G is as we go through the different problems, and also as well as F, and we'll talk about the different states that are defined by each input. All right, so let's start with looking at contiguous sequences in 1D. I just want to point out that we talk about specifically contiguous as meaning connected, right? We are not talking about something like subsequences here. Subsequences, let's say you have a string string, so a contiguous subsequence is connected, right? So str checks out, it is a contiguous subsequence, but something like srn, let's say, right? That's a valid subsequence, but it is not a contiguous sequence. Okay, so these patterns work well when you're dealing with partitioning something that happens to be connected. But not all the time. It depends on the problem. But oftentimes you'll see this type of pattern when you deal with contiguous sequences. You're going to be dealing with substrings and also subarray problems. All right, So this is the first one. Fi depends on an entire range of increasing size. The example I love most for this is probably the longest increasing sequence problem. It is LeetCode 300. And basically the recurrence relation for each, well, if you don't know that problem, I encourage you to look it up. We've talked a little bit about it before on previous presentations, but it is probably one of my favorite ones, and most of the solutions end up with a recurrence relation where the current I actually has to find the, for each current I, you basically try to find the previous subsequences ending at index j, where the value of j was strictly less than a of I, right? So there is some way to combine basically the computation from 0 all the way to I minus 1 of taking f over that entire range of input. So we're not going to talk about the bottom-up scheduling. If you saw the previous presentation, which was how I generalized depth first search into recursion trees, then you'll kind of get a feel for what this is, but don't worry if you don't understand what bottom-up scheduling means right now. We're just going to be focusing on mostly top-down solutions today as it is. So these are two different patterns of writing a recurrence relation for this type of pattern. So each I, as you move forward, depends on all the previous computed things in that range. Right? That's the prefix version. Right? Why is it the prefix version? It's because for f of I, you depend on solving some kind of prefix over that input, right? And similarly, this is the suffix version because f of I depends on what happens later, right? So let's say you have an array of numbers, 1, 2, 3, 4, 5, 6. F of I, right, the answer to this problem right here is phrased in terms of the mappings of f of 0, 1, 2, so f of 2 and f of 3 and f of 4 here, and finally f of 5, right? So this would be a suffix version of looking at the longest increasing subsequence, where for each index you try and find an index with some length where 2 is less than some number, some value that happened at an index that happened further, that happened to the right of your current index of 1 in this example. All right. So you've also seen this kind of recurrence relation or pattern in the hash maps lecture. TwoSum was the first example where we practiced this, and g of x was kind of like a hash map lookup over that range. And here's a brief overview of TwoSum. If you kind of forgot what it was, it's basically if you have two numbers, and if you needed to sum up to some target, right, equal to 7, and whether you could find two numbers that equal 7, I see a pair right here, right? So as you keep increasing I, right, this 2 depends on finding something over on the previously seen part of the input, where we keep track of some of our answers. Yeah, so finally when you get to 5, you're going to look through this entire range, and because a hash map lookup was O of 1, this ends up in total being O of n time, right, because we're just enumerating over nums and incrementing as we keep looking at more nums. All right, we're going to come back to this pattern for sure. You're definitely going to see this in longest increasing subsequence. All right, one note on the time complexity for this is that in general, it's kind of like the time it takes for G times the time it takes for F. And if the computation over that range can be done O of 1, like perhaps with a max operation, right? You only need to take in the newest input when you do a max, and that's going to be max over that entire range. You can actually shave down your time complexity, right? So in 2-sum, the time complexity is just the time to basically go through the entire array of numbers. All right. We're also I know I said this was about patterns for contiguous sequences, but you'll also find another very common pattern that you're going to look at maybe not the contiguous answers, but you're going to increment I contiguously, and you're going to look at certain subproblems, right? So this would be the one where you depend on a particular prefix being known, right? F of I needs to be computed, or of course, if you're doing top-down, to compute Fi, you're going to just go down another recursion stack and compute F of I minus 1. There's a lot of variations. I think some of the most important variations for this revolve around jump game. There's jump game 1, there's jump game 2, and there's also a bunch of others that follow this pattern within the jump game series of problems on LeetCode. I think they are great practice. And it's not always just this one state of like, oh, I only need to care about this for, if I'm at I right now, I only need to care about this one, right? Of course, there's variations where you relate the current subproblem perhaps to combining. Maybe that combination is adding, maybe it's something else, maybe it's conditionally combining something. Might be I minus 2 or something like that, but there are some finite amount of states. Just to give you an example, we went over this problem last time, but jump game 2, for example, has a relationship such that for f of 0, right, you care about the answers to combining f of 1 and also f of 2, right? And it just so happens that f of 1, right, is the result for f of 1, right, the minimum number of jumps to reach the last index, is going to be related to this subproblem right here, this subproblem right here, and this subproblem right here. So that would be f of 2, f of 3, as well as f of 4, finally. Yeah, I think I meant to show this jump game problem instead. But it's very, very similar as a problem. So last time I showed an O of n squared recurrence relation, and that is essentially kind of what this looks like here, is that for each subproblem I am doing basically a loop, right, to find all the related subproblems. For this one, you can also write a recurrence relation that is O of n, and this recurrence relation, f of 0, is really just based off of combining only one subproblem, right? The trick to this is that f of 0, if f of 0 is true, it means that the right bound that you are extending must be able to reach the right index when you go into the next index. So for each subproblem, right, the subproblem mainly being defined by the particular index that you're at within the array, you get the chance to extend the right bound, right? This is the farthest you're able to go. And so basically, doing all this is basically the G right here. And it's got a conditional in it. Actually, these are base cases, right? These are base cases, and you combine against only one subproblem, right? Because if you're able to get to the last index, you return true. But of course, if you are not able to go into the next, if this index is currently over the acceptable right bound, right? Maybe the farthest right bound you can get is here. You're not actually able to start this particular subproblem, right? So then you return false, right? So whichever index that you're at, let's say this is some index at I, and you want to get to I plus 1. If the furthest right bound that has been computed is less than I plus 1, then you're not actually able to go to that next index, right? So this is a different recurrence relation, right? The one that I showed last presentation was actually n squared. This one you can tell basically this is O of n, right? Because you only depend on the result to one subproblem, and this G does basically just a constant number of operations. All right. So this one is also a very popular recurrence relation. You're going to see this as a little bit, it's very related to pick or no pick dynamic programming pattern. This is basically, we're going to, at I, extend a partition. That is, we are going to include more and more things from I until, let me represent it this way. So you start at I, right? And you have some kind of window that you're extending, right? You see this here, S in range of 1 to T, right? T being the max size of that window. So let's just say we're at like some S right here. And basically once we're at S, right, we accumulate some kind of result. Maybe this is a max operation, maybe it's a min operation, maybe it's something else entirely. And then, because you've gotten this subproblem right here, right, you're accumulating some kind of result, and then you start a new partition, right? This is going to be starting at I plus S, actually. I'm going to take this S, right? It's going to be over here, and actually this one, I should have more accurately drawn this, or this is what it really was. It's really I to S minus 1 that is partly here in this problem, and it's the accumulator result, right? We've done some computation over this partition, and then there is the subproblem, and we're not going to worry about it, right? That subproblem starts at I plus S, right? And that is right here where I have my yellow pen. And of course, this subproblem is then free to do as it pleases and start a new subproblem going on this way. And you can see how next iteration, basically you're going to extend here, and this one in teal is now going to be properly from I to S, and then the yellow partition starts at S plus 1. Okay? And so this is a type of recurrence relation where you have these overlapping subproblems, right? You can imagine as this keeps growing, the subproblem that started in this salmon color is going to be reached yet again, right? Let's say finally, right, the teal, it gets this big, and then the yellow starts over here. Well, we'll have computed the subproblem at S, at I plus S, right? So you can see how there's overlapping subproblems, and as long as there's a way to combine these subproblems that is the same for each nested subproblem. So hopefully you're able to visualize that. We're definitely going to see quite a few problems today on this recurrence relation. If you can identify this pattern, you are generally looking at problems that are between medium and hard. If you care about things like difficulty ratings, I've found that a lot of the zero-track ratings for problems that deal with this kind of recurrence relation are at least in the 2000 plus range. So legit hard problems. But with patterns like these, hopefully they'll start feeling like mediums. The time complexity is generally n times the window t. Since for each subproblem I, right, that you saw up here, there's going to be n states, right, for this I. And for this range, well, if this t was maybe n, and a lot of times it is, then for each index, you're doing a for loop forward, right? So you can expect something like n times t or n squared if t equals n. The space complexity that you're going to need for this is only O of n, because you're going to cache based off of the problem state, which is defined by this index I. We'll talk more about like these different problem states and identifying them. We'll definitely practice that today. All right, let's move on to contiguous sequences in 2D. And something to mention is that once you get into 2D and higher dimensions, the patterns are going to be fuzzier, right? They're going to be fuzzy because you're just going to have more variation on how G works, right? Once you start having more parameters, right, for a problem, the interconnectedness of them is actually going to increase, right? Which leads to more cognitive complexity, and in some, all that means is just like, yeah, they're going to feel harder. Just because you're going to deal with more moving parts. A lot of times for these contiguous sequences, we're going to deal with two different dimensions, I and j, and it depends on the problem, right? There might also be another additional parameter to it, or in addition to just I and j, depending on the problem, you might also deal with other complexities, right? But we're going to stick with just simple ones. I think I only have I and j today for some of these patterns. All right, so this is one of my favorite ones because it's pretty easy to visualize. One thing that you do is once you have your I and j, right, and you're basically computing f of I over j, you're just shrinking the interval bounds, okay? So I might just move a bit forward, oh, whoops, right here, right? This might be a subproblem where you have I minus 1, right, all the way at j, right? And you might also shrink it on the other way around, right? So you might move this way as well. And then you'll have here, which is j minus 1, but you'll also have, again, I, okay? So you have this subproblem, right? The one in salmon color, and you have this subproblem, the one in yellow color. And you can start to see how these problems are going to overlap, especially when I bring in this last one right here that I'm going to write in green. This is shrinking both sides, so you're going to be over here, I minus 1, and you're also going to be here, j minus 1, right? And it's very easy to picture, oh, what if for here, this green, what if the next move you make is going to be just shrinking the right bound, right? Well, that's the similar subproblem to if you, let's say, did this, if you started with this yellow, and the next thing you did at yellow was shrink the left bound, right? All of a sudden, that starts looking very similar. It's very easy to see that you have a bunch of overlapping subproblems when you do this. And notice that even though, in my notation, even though I comma j is a range, I'm relating it immediately to every subproblem, right? I'm just talking about the adjacent subproblems with this notation, right? These adjacent subproblems, of course, will eventually compute the answers of what's needed from the entire interval of every single pair of I crossed with j for a complexity that is usually O of n squared, right? Because there's n variations for I and there's n variations for j. That's not strict, of course. A lot of these problems, I cannot ever actually be greater than j, but this is just very rough time complexity for you. All right. This is where I explained what I just said. And this is another one that hopefully you read the pre-work for this presentation. It was, as I assigned on Discord, chapter 3 of Jeff Erickson's book on algorithms. It's open source, but I linked you to chapter 3 on dynamic programming, where he goes over at a distance in quite some detail. And it is really probably the text that you should start with when you start reading about dynamic programming. I haven't seen anyone do a better job than Jeff Erickson. So anyway, an edit distance is basically a model for this type of pattern. You basically have two sequences, right? You have word A, and you also have word B, right? Word A might be the word apple, and word B might be the word apply. And your job, right, in edit distance, is simply to find the minimum amount of operations to make both of the words equal. That is, if you scratched off E and you made this a Y, that would be a replacement operation. There are three operations for edit distance. One that we just went over is replacement, another one is insertion, and the third one is deletion, right? You can delete a particular character. And this is really that pattern. Edit distance actually fits a lot of different types of problems, as we'll see. And I generally, for these problems, pick the suffix version. I start my computing my f at 0, 0. So I is at 0, j is at 0. And what this would mean here is that I equals 0, let's say j equals 0, right? And if I want to compute the edit distance of this entire string, what I'm going to need is three different subproblems. I'm going to need, well, what is the distance between apply and maybe pp, sorry, let me change the string back, of apple and pply. And I'm also going to care about, well, what is the edit distance if I just take pple, right, that's this middle one. If I pick the suffix of that word, pple, and compare it with just apply, right? This would be a delete operation on word A, right? This one happens where we might actually just do a replacement, right? And a good example of that is actually probably like the last one. But you could actually replace A if you felt like you needed to. But in this case, we don't. It might make sense more if like this was a completely different character, right? Like zpple. But anyway, I don't want to get too deep into the weeds there right now. This is the suffix version. You start at 0, 0, and your answers are basically these subproblems defined by the suffixes of the two strings. The prefix version is you can start at, there's a typo here. This is length of A minus 1 and length of B minus 1, right? This is when you start at the last index, right? And then your answers are based off of the prefixes, right? Based off of the prefixes of these two strings. And we're not going to really worry about bottom-up scheduling today. So I wrote some stuff, but you don't have to worry about it too much today. And all right, so I'm actually not going to worry about this slide too much. Sorry, I didn't have like all the time in the world for a lot of my slides. We are covering quite a bit today, and we're actually going to cover that pattern inside pick or no pick, so don't worry about that. There's divide and conquer halving. We're not going to really talk about problems of this nature today. A lot of those problems aren't going to be dynamic programming. A at least not for the problems that I've worked on personally, and I don't have great examples. But you see this in binary search even, and merge sort and quick sort. And generally that's going to look like something like this, where you're going to be splitting that subproblem in halves and then looking at answers to the halves. There's divide and conquer, which I call with linear cut point, but I'm not sure if like there's canonical literature on this, but definitely the matrix chain multiplication type problem is kind of the poster child of this. And this problem has you explore a partitioning on the left and right side and optimizing over it. So basically, you're going to deal with a particular problem, right, between I and j. And what's going to happen is that, oh, you're going to go until I until k, right? But then k moves, right? Well, I'm going to try this k this time, right? And then here is where you do the recursive call, right? Here is also where you do a recursive call, right? And your G basically combines these two different recursive calls. It's not always two calls either, like it could be more. But this is the matrix chain multiplication type problem. And you explore every partitioning of a left and right side in a subarray. This is different than that previous recurrence relation where I showed you, where you just have your fixed start, right? And then you accumulate here, but then you recurse over here, right? That's different. This is a different pattern than this. I would say that when you deal with problems like these, you're generally dealing with even harder problems than problems that look like this. I have only one problem to show you with this pattern today, and we might not get to it, to be honest. But here is what it looks like if you want to look at it. You just combine the subproblems from the left side of the midpoint and the right side of the midpoint. In general, for these types of problems, the time complexity is going to be n cubed. Again, with I and j, every pair of I and j has n squared states, and then inside there you're doing a for loop, right? And we're assuming that these subproblems are cached, right? Which is why which is why I'm claiming n cubed. So the space complexity, however, is going to be n squared. Again, you can kind of check with the amount of states that you have. This isn't always necessarily the case, but it's a good heuristic to keep in mind. I'm not going to say too much more about that. All right, this pick or no pick pattern is super, super powerful. If there's just two patterns I want you to like really get good with by the end of today's presentation, pick or no pick is one of them. The other one is basically Contiguous Sequences 1D, the first one that I showed you. And well, if I were to pick a third one, you should really understand the recurrence relation for edit distance. Yeah. Anyway, let's move on. Pick or no pick, right? This is a pattern that helps you solve the famous knapsack problem. If you don't know what the knapsack problem is, I do encourage you to read this problem. I'll just give you a rundown of what it is. Feel free to skip until I'm not looking at Wikipedia. So this knapsack problem, basically you want to grab a bunch of loot, right? But your knapsack, right, only has a particular weight limit, right? But you want to get as much loot, much valuable loot as possible, right? So it's an optimization problem over a constraint, right? There's many different variations of this. Sometimes you have unlimited copies of something. Sometimes there's only limited copies. And basically you need to be under the weight limit. Like you can't just like go over the weight limit, right? That's not allowed. So basically off of a set of things, what you're doing really is you are optimizing a subset, okay? So the choices that you're going to be making when creating that subset aren't going to necessarily be contiguous, right? You might choose a little bit of this item and some of this item and one of this item, right? Which might be spaced much farther away from each other inside some kind of array, right? So you're optimizing basically the value of a subset, right? And this pick or no pick pattern is really powerful, and it yields itself to, well, it is one of the ways to solve in the knapsack problem. And be warned that sometimes, like this pick or no pick pattern, generally you're probably going to look at a linear product of usually two parameters. So it's not going to be just linear, it's going to be a product. So this pattern works for partitioning problems as well. So keep that in mind. And there's actually two ways that I like to write this pattern. One of them is just the explicit multiple calls pattern. We've talked a bit on this when talking about backtracking, the previous presentation. And this, maybe I encourage you to do this one a bit more. I also tend to use the for loop or while loop pattern, which is a lot like that contiguous sequences 1D kind of thing. But don't worry too much about that. We'll see examples. This will make more sense once you start seeing specific problems. So the explicit multiple calls, at least if you're familiar with the backtracking version, is going to be we do something to the accumulator, and then we do the recursive call, right? This is where we do the recursion. And then we usually, reverse the operation on the accumulator. If we are, building a sequence, perhaps this is an append operation. If you're familiar with Python, this is just adding something into a bag, a list. And here you might just remove the last element that was pushed onto this accumulator, at least as part of this recursion stack. And so there might be other candidates to pick or not pick. So this is what picking looks like, right? You actually do pick something that happens at this index I. And this is what it looks like to not pick, right? So this is no update to the accumulator. You just full on skip, right? You skip the choice, right? You don't update the accumulator. Note that the form that this is written in is more conducive to backtracking, but pick or no pick can also be used, as we're going to talk about today, in dynamic programming problems. And this example doesn't look exactly cache friendly because you do need, when you are returning, when you do recursive calls, right, f of k, f of k minus I or something, right? These results, they need to eventually bubble back up, right, in order for f of k to actually combine all of these subproblems, right? All of these subproblems, okay? So just keep that in mind when you write pick or no pick. The functions definitely have to return something, right? So the loop version of this, I adapted this from one of the problems today. One of my comments kind of spoils which problem it is. But basically, when you go through a list of items, right, and you're choosing a subset, so this is how this works. If you don't pick something, then basically what you're saying is, hey, for this current I, I'm going to instead start a new partition, right? I'm going to start a new partition, and this new partition can decide to also do roughly the same thing, to pick or not pick this, and also advance, get the subproblem over here, perhaps, right? So we're in teal right now, right? We are in the color teal. We are in this left side of the subproblem. And now not picking, right, is the start of the one in salmon, right, is this subproblem right here. We are doing f of I right there. And we get the answer and then we accumulate it, right? We accumulate what would happen if we did not pick this option as part of the current partition. When we go and increment it, that's when we update our index and we update our accumulator, right? Actually, this index update happens here. But we update our accumulator by including this I currently, right? So you can see how basically for this teal, everything in teal, right? You already explored the option to not pick this current I, right? To not pick this current I, and what it is like to pick it at the current f of I, right? So this is pretty similar actually to that contiguous partitioning problem as well. And I think I mentioned this is really related. You might find that sometimes this pattern works well for the pick or no pick, and sometimes it doesn't work as well as the explicit multiple calls. Yeah, but we will go through some examples. And, you know, sometimes it's style, and sometimes it does make a difference. This pattern is explicit grids with limited direction. I want to stress the limited directions piece, and this pattern works well when you deal with a directed acyclic graph. We talked about dynamic programming when you have a graph in general, right? And you need to minimize something like, a shortest path, right? Or the minimum cost to go somewhere, right? From a source node to an end node. Dijkstra is really one of the things that should come to mind and be part of your toolbox when attempting to start, when you view certain problems like that, right? Because Dijkstra deals with graphs that can be cyclic, right? It has that ability. The recurrence relations that we're going to talk about in this pattern aren't going to have cycles, and you can do something that's going to be faster for that. The robot coin problem is how I first learned about it a long time ago when I first took algorithms in college. Maybe also Pascal's triangle is also a really good example of this. And this pattern works by, looking at every single cell grid. And this is just 2D, but of course you can have grids that are 3D as well, in which you would have 3 dimensions instead of the 2. But we're just going to stick with 2D grids today, but you can probably generalize this pattern to more dimensions. And basically the way to get the answer to add a particular row and column is to know the answers to the immediate neighbors that this row and column need. Okay, we'll see explicit examples of that, so don't worry too much. I have easier examples for this type of pattern, but there are quite difficult problems that I still haven't done on LeetCode. All right, we won't cover state machine dynamic programming. I think there's a few problems on LeetCode, but not that many on this type of pattern. Dijkstra, I just want to go over because I want to hit home that this is dynamic programming. It doesn't look like depth first search at all. So basically you want to get from P all the way to Q. Along the way, some shortest path, no matter what it is going to have some perhaps empty subset of nodes, right? That go all the way to Q, right? But how does P get to Q, right? P is only allowed to visit its neighbors, right? And Q must be arrived at from its neighbors, right? There's no other way to get to Q other than Q's neighbors. And what we do is actually, if we have the shortest path of the neighbors of Q, then if we take the one that has least cost, or the multiple ones that take the least cost, if there's multiple shortest paths, but let's just say without loss of generality that there's going to be only one shortest path. So we take the one that has the least cost, right, going to Q. But how do we get to the ones with the least cost? Well, we look at its neighbors, right? And what was the least cost in order to get to these different neighbors, right? And that's really the recurrence relationship described in English that you're really going for. you have overlapping subproblems because there's going to be multiple ways to arrive at, maybe a particular node. And we might also try and explore the same neighbor again and again after we've already visited, but we cache our results onto what the shortest path it took to get to perhaps this node that I'm circling right here was, right? That's how subproblems overlap, is we might have to visit a node again, but if we've already visited it once, we already know we can prune that part of the search tree. And the shortest path at Q, right, this is the optimal substructure, right, from P to Q, has to be reached from a neighbor of P, assuming that there are neighbors, right, and that Q isn't the shortest path. Right, and so for each n sub I between P and Q, we build the shortest paths to P to each n sub I, and we use those results to reach Q, right? The fact that that's possible, that the shortest path must come from other shortest paths, that's the optimal substructure property. I linked to this property beforehand, probably in the previous lecture, but if not, Wikipedia has a fairly good article on it. I recommend you check it out. All right, so in Dijkstra, if we were to use this notation, what would it look like? Well, the shortest path from P to Q must occur from the shortest path of the neighbors n sub 0 to n sub k, and how they have the shortest path to Q, right? So this is the suffix version of writing this. And G is some variation of min, and we talked about Dijkstra, I think, 2 presentations ago. I'm not sure if I have that uploaded yet. But make sure, G also makes sure not to repeat cycles, right? We used a mechanism like a min cost table in order to avoid repeatedly visiting a node and then its children, right? So this is very loose notation of using G. G is just my way of combining subproblems. All right, so finally, we are here. We are ready to see some problems to practice.